Hello, everybody. I'm Claudio Ferrari, and together with two of my co-authors, Jeremy Scheurer and Louis Tudembon, I will present our work on semantic segmentation of histopathological slides. The motivation behind this work is that there exists a skin disease called mycosis fungoides, which is a form of skin cancer and is potentially life-threatening. But the problem is that in its early stages, it strongly resembles benign skin eczema, which is a form of dermatitis, and you get a rash in your skin and it itches a little bit, but it's not, it's easily treated and it's not a problem. So we have those two diseases, and so it's of paramount importance to be able to distinguish between the two to increase patient survival chances that actually have MF. We, coming from the machine learning side, we asked ourselves if and how machine learning could help in this diagnostic pipeline to improve or simplify the diagnostic process. So the way diagnosis is done today is you have this skin disease on the left. In this case, it's actually MF. And then a skin biopsy is taken, thinly sliced and put on glass slides and also stained with a solution to make the different parts of the tissue visible in different colors. And at the last stage, it's looked at under the microscope by trained specialists. And actually in this stage, because here it's an image analysis task, we thought that maybe we can devise a solution by using machine learning, because we have seen huge successes in recent years in image analysis using machine learning. So this is what our data actually looks like. On the left, you see an example of such a whole slide image. In our case, it's actually a hemotoxylin eosine stained image. This is why you see this purplish color. And we have 164 of them. 60 cases correspond to MF, and 104 cases correspond to eczema. And we were very lucky to be able to partner up with the Institute of Kempf and Pfalz on this. They are specialists in this field. This is an institute located here in Zurich. And they not only provided us with data, but they provided us with pixel-wise annotations of regions of interest. So this blue and red thing on the right, you see, if you overlay that on the picture, you could see that it's actually just an outline of certain regions. So in red, we have the epidermis region, which is the outermost region of the skin. And in blue, we have so-called spongiotic tissue or spongiosis. Those are regions within the epidermis with an abnormal amount of intercellular fluid. And why those two regions specifically? Well, the specialists use those two features as key features in distinguishing if a skin sample is MF or it's just eczema. And so we applied machine learning in two stages to this. In the first stage, we have the whole slide image as an input, and we try to predict this segmentation map on the right. So we try to devise a model that finds a pixel-wise segmentation map of epidermis and spongiosis. In the second stage, we try to use that information together with the original image to devise a model that classifies a glass slide into the classes MF or eczema. And so in the next few slides, Jeremy will tell you more about the segmentation part of our machine learning model. And then in the last few slides, Louis will illustrate how we combine this with the original image to devise a classification model. So I will now hand over to Jeremy to explain the segmentation model.
Okay, so I'm going to explain how we designed our architecture to solve the semantic segmentation task. So we built our whole model on the idea of a UNet, which is very commonly used for semantic segmentation tasks. And in its core, it has this UNet shape, this U shape, where in the beginning we have down convolutions with max pooling layers to extract important features of the image, and then we have up convolutions to make the output of the same size as the input again. Now, what we changed is the whole encoder part of this UNet, where we used an efficient net. And if you're not familiar with that, the efficient net is just an architecture that was specifically designed by algorithms, that is not by humans, to solve specific image tasks. And it was able to achieve, at the time, a new state-of-the-art on the ImageNet task. So in short, it's just a really good architecture to extract features from images. And so basically, we just use this as our encoder and call this whole architecture the EUNet. To make sure that this is actually sensical and that model makes sense, we applied this model to a different task of another paper where we actually also have histopathological slides, but only two classes, epidermis and everything else. So compared to our task, this was a two-class problem. And there we applied our model to make sure that it actually gets good results. And this was actually the case. We were able to get very comparable results to theirs. Unfortunately, the whole setup of the training data set, the pre-processing and post-processing was slightly different to theirs, so we couldn't exactly compare it. But the main goal was just to make sure that our model actually makes sense. And now we can have a quick look at the results. So as we can see, we compared our EUNet to a simple UNet model. So this is just the one proposed in the original paper. And we can clearly see that for the semantic segmentation task, we clearly outperform a normal UNet in the important metrics of the mean IOU, mean intersection over union, and the Matthews correlation. On the right-hand side, we want to show you how such predictions actually look like. So at the top, we have an input image slide. Below on the left is actually the label that was annotated by pathologists. And on the right, we can see the prediction of our EUNet. Now, naturally, this is only one example out of many, but we can clearly see that our model is able to recover most of the important pixel annotations. And now I will hand over to Luis, which will then talk about how we incorporated that to make classification predictions.
Okay, so now I'll explain briefly the second part of our papers, which is actually distinguishing between eczema and MF. So we utilized the previous semantic segmentation map and the network that we created to create this end-to-end solution that essentially takes an input image from one of these slides and generates the segmentation map, and then it concatenates with the original image. And this junction of both, we then use some down convolutions and max pooling layers to actually perform classification to distinguish between eczema and MF. So in this slide, we can look at the results more closely. We didn't develop one model. We developed two models, which we named binary cross entropy and cosine similarity, due to their loss functions that we used. So this is essentially the same model trained with different loss functions that achieved two different local minimum. And we can see that this task is actually very, very hard to classify. And we show in this table a baseline model, which is two baseline models, which are predicting always the same class. So since there was some class imbalance in our data, we can see that these values aren't 50-50. And in both cases, the models that we created are above baseline, but not too much. So these models still aren't capable of replacing trained pathologists to classify between these two diseases. but they are actually helpful in some scenarios. For instance, the binary cross-entropy model could be used in routine checks where pathologists aren't available, because this model will not generate too many false positives. And model cosine similarity could also be used to filter out obvious negative cases, so eczema cases. And we also performed an ablation analysis. So we verified that the existence of the segmentation map was actually contributing useful information to the classification. And so without changing anything else to our model, we removed the segmentation map as an input, and we can see that the results drop across the board. Thank you very much for listening to our presentation.